How did the universe begin? It's one of the oldest questions humans have ever asked. We know that about 13.8 billion years ago, everything we can see today, every galaxy, every star, every atom, was packed into a state that was incredibly hot, incredibly dense, and expanding. We call that moment the Big Bang. But here's the part that quietly unsettles physicists. If time itself began at the Big Bang, then what does before even mean? Asking what came before the Big Bang may be like asking what's north of the North Pole. It sounds reasonable until you realize the question itself may not apply. Over the years, scientists have proposed many ideas. Some suggest there was a phase before the Big Bang. Others believe the universe may go through cycles. And some argue there was no before at all. None of these ideas is final. And that's exactly why this story matters. This video won't give you a simple answer. Instead, it will gently take you backward through time, layer by layer, until the universe begins to explain itself. To understand how the universe began, we first have to ask what beginning really means. When physicists talk about the beginning of the universe, they don't mean an explosion in empty space. In physics, the word beginning means something much stranger. One possibility is that time itself began with the universe. In this view, there was no before, because there was no time for anything to exist in. The universe didn't appear in time. Time appeared with the universe. Another idea suggests that the Big Bang was not the true beginning, but the end of an earlier phase. A period of rapid expansion, known as inflation, may have prepared the universe before the hot, dense state we usually call the Big Bang. Some models go even further. In cyclic or big bounce universes, expansion is followed by contraction again and again across immense spans of time. The universe may not have begun once, but many times. Physicist Roger Penrose proposed a different approach. In his conformal cyclic cosmology, the extremely old universe and the extremely young universe begin to resemble each other. When everything becomes either infinitely large or infinitely small, certain distinctions may disappear. And in string theory, the Big Bang could be the result of a collision between higher dimensional structures known as branes. Our universe may have been created not from nothing, but from an event in a larger reality. Each of these ideas tries to solve a different problem. None of them answers everything, and none of them has been proven wrong. This is not a weakness of science. It's how science works. By allowing multiple explanations to exist until nature itself chooses between them. But here's the important part. No matter which idea turns out to be correct, they all agree on one thing. The early universe was once extremely hot, extremely dense, and unlike anything we experience today. That shared conclusion is where the story becomes clear again. Where is the hottest place in the universe? It's not the core of a star, where nuclear fusion burns for billions of years. It's not the heart of a supernova, briefly brighter than an entire galaxy. And it's not even the most powerful particle accelerators on Earth, where protons collide at near light speed. The hottest place in the universe no longer exists as a place at all. It existed as a moment. To understand that, we need to rethink what temperature really means. Temperature is not just about heat you can feel. It's a measure of energy. How violently particles are moving, how tightly energy is packed into space. As we trace the universe backward in time, everything becomes smaller. And as space shrinks, energy density rises. Keep going far enough, and you reach a temperature so extreme that our usual numbers almost stop making sense. This is known as the Planck temperature, about 1032 degrees Kelvin. That's a number with 32 zeros after it, far hotter than the center of any star, far hotter than any explosion physics can recreate. At this scale, the universe was compressed into an unimaginably tiny volume. Every bit of energy that now fills billions of light years was once concentrated into a region far smaller than an atom. To describe that moment, physicists use what are called Planck units. The Planck length is the smallest meaningful distance we know how to define. The Planck time is the shortest meaningful tick of the cosmic clock, the time it takes light to travel one Planck length. Before this point, space and time behave smoothly, like a calm surface. At the Planck scale, that surface begins to break apart. Space may no longer be continuous. Time may no longer flow in a familiar way. The equations that describe gravity and quantum mechanics stop agreeing with each other. This doesn't mean the universe stops existing. It means our descriptions stop working. What we call the beginning is not a clear starting line. It's a boundary, a limit beyond which our current understanding cannot go. And the closer we move toward that boundary, the stranger the rules become. At this extreme scale, the universe wasn't just hot. It was fundamentally different. A place where space, time, and energy were no longer separate ideas, but part of the same unresolved whole. And stepping across that boundary takes us into the earliest chapter we can even attempt to describe. The earliest era we can even name has a very precise boundary. It's called the Planck era. This is the first tiny fraction of a second after the universe began, less than 10 to 43 seconds. A moment so brief that it defies ordinary intuition. During the Planck era, the universe was not only unimaginably hot and dense, it was governed by two sets of rules at the same time. And those rules do not agree with each other. On one side is general relativity, which describes gravity as the smooth bending of space and time. It works beautifully for planets, stars, and galaxies. On the other side is quantum mechanics, which governs the behavior of particles at the smallest scales. It describes a universe that is probabilistic, jittery, and never perfectly still. In the Planck era, gravity was as strong as the other fundamental forces. Quantum effects were not small corrections. They dominated everything. And when gravity becomes quantum, our equations stop making sense. Space and time themselves may not have been smooth at all. Instead, they may have behaved like a restless surface, fluctuating, bubbling, and unstable. Physicists sometimes describe this as quantum foam, a state where distances and durations cannot be sharply defined. In such conditions, familiar concepts lose their meaning. There may have been no clear separation between past and future, no stable geometry, no fixed structure the universe could settle into. This is why we cannot directly observe the Planck era. Any signal from that time would be scrambled beyond recognition. Our experiments cannot recreate energies even remotely close to those conditions. And without testable predictions, physics reaches a hard limit. Still, scientists continue to search for a deeper framework. Some explore theories of quantum gravity, trying to unite relativity and quantum mechanics into a single description. Others look for hypothetical particles known as gravitons, which would carry the force of gravity at the quantum level. And in string theory, the fundamental ingredients of reality are not point-like particles, but tiny, vibrating strings existing in higher dimensions. None of these ideas has been confirmed. And that uncertainty is not a failure. It's an honest boundary. Ironically, the most important moment in cosmic history is also the one we understand the least. The era that shaped everything that followed is the one we cannot fully describe. But the universe did not remain in this state for long. As space expanded and the temperature dropped, the chaos of the Planck era began to fade. The rules slowly became simpler, structures began to emerge, and as the universe cooled, something remarkable began to happen. As the universe emerged from the Planck era, it was still unimaginably hot. Hotter than any star, hotter than any explosion we can recreate. But something important had begun to change. For the first time, the universe was cooling enough for its underlying rules to take shape. Today, we describe nature using 4 fundamental forces: gravity, which shapes the motion of planets and galaxies; electromagnetism, which governs light, electricity, and chemistry; the strong nuclear force, which binds atomic nuclei together; and the weak nuclear force, responsible for radioactive decay. These forces feel distinct to us now. They behave differently. They operate at different strengths. But in the early universe, that distinction did not exist. At extremely high energies, the forces were unified, indistinguishable from one another. They acted as a single, combined interaction. A helpful way to picture this is a spinning coin. When the coin is spinning fast enough, you can't tell heads from tails. Only when it slows down do the 2 sides reveal themselves. The early universe was like that spinning coin. At high energy, the differences between forces were blurred. As the universe expanded and cooled, those differences began to appear. The first force to separate was gravity. While the details remain uncertain, gravity appears to have broken away before the others. From that moment on, space and time could begin responding to mass and energy in a consistent way. As cooling continued, the strong nuclear force separated from what physicists call the electro-weak force. That left electromagnetism and the weak force still united, behaving as one. Only later did those 2 finally part ways, becoming the familiar forces that shape atoms and radiation today. These transitions were not gradual adjustments. They were more like phase changes, similar to how water suddenly freezes into ice. Above a certain temperature, everything behaves one way. Below it, entirely new properties emerge. This means the laws of physics were not always what they are now. They are not fixed background rules that existed forever. They are the result of the universe cooling through specific energy thresholds. Physicists have long searched for a deeper explanation of this process. Theories known as grand unified theories, or GUTS, attempt to describe how the forces merge and separate within a single mathematical framework. So far, none has been confirmed. But even without a complete theory, the consequences are clear. As the forces separated, the universe became predictable for the first time. Cause and effect began to follow stable patterns. Particles could interact in consistent ways. Structures could persist instead of dissolving instantly back into chaos. This was a turning point. The universe was no longer governed by a single, overwhelming blur of energy. It was beginning to organize itself, step by step, into a place where complexity could eventually arise. And yet, when physicists tried to take these newly formed laws and run them backward toward the beginning, something didn't add up. By now, the Big Bang sounds like a success story. It explains why the universe is expanding. It explains why distant galaxies are moving away from us. It explains the faint afterglow of heat we still observe in every direction. The cosmic microwave background, glowing at about 2.7 degrees above absolute zero. But when physicists looked more closely, something felt off. The Big Bang explained a great deal, but not everything. One of the first cracks appeared in what's known as the horizon problem. When we observe the cosmic microwave background, we see that regions of space separated by vast distances have almost exactly the same temperature. The problem is that, according to the classical Big Bang model, those regions were never close enough to exchange information. There simply wasn't enough time for heat to spread evenly across the universe. And yet, the universe looks astonishingly uniform. Then there is the flatness problem. When physicists measure the large-scale geometry of the universe, they find that it is remarkably close to being perfectly flat. Not curved inward, not curved outward, balanced with extraordinary precision. To get a universe this flat by chance would require initial conditions tuned to an almost unbelievable degree. A tiny deviation early on would have grown dramatically over time. But it didn't. There is also the monopole problem. Certain theories predict that the early universe should have produced large numbers of magnetic monopoles, isolated north or south magnetic charges. These exotic particles would be massive and long-lived. And yet, despite decades of searching, none have ever been observed. Each of these issues points to the same uneasy conclusion. The classical Big Bang model, taken on its own, seems incomplete. This doesn't mean it's wrong. The Big Bang remains one of the most successful frameworks in all of science, but success does not mean finality. What troubled physicists most was not just that these problems existed. It was that the universe appeared too orderly, too uniform, too balanced, too carefully arranged. Not in a philosophical sense, but in a physical one. The early universe looked less like a random outcome and more like a system that had been carefully prepared. That raised a deeper question. Was there some process that smoothed out the universe before the hot Big Bang phase we normally describe? Was there a mechanism that erased irregularities, flattened space, and diluted unwanted relics, all before atoms or light ever existed? If so, the Big Bang might not be the true beginning of the story. It might instead be the aftermath of something even more dramatic. At this point, physicists were faced with a choice. Either accept that the universe began in an extraordinarily special state for reasons unknown, or search for a new idea that could explain why it looked that way in the first place. That search led to a radical proposal, one that suggested the universe didn't just expand. It may have expanded in a way unlike anything we see today. To fix these problems, the universe may have done something extraordinary. In 1979, a young physicist named Alan Guth proposed an idea that sounded almost unbelievable. He suggested that, very early in its history, the universe went through a brief but extreme phase of expansion, a phase now known as inflation. This was not an explosion of matter into space. It was something far stranger. Space itself expanded. During inflation, the distance between points in space increased at an enormous rate, far faster than the speed of light. This does not violate relativity, because nothing was moving through space faster than light. Instead, space itself was stretching. A simple way to imagine this is by folding a piece of paper in half. Fold it once, and it doubles in thickness. Fold it again, and it doubles again. After about 90 folds, the paper would be thicker than the observable universe. Inflation works in a similar way. In a tiny fraction of a second, space doubled, and doubled again, and again, smoothing and enlarging the universe beyond recognition. This single idea solved several problems at once. The horizon problem disappears because regions that now seem far apart were once close together before inflation stretched them apart. They had time to reach the same temperature. The flatness problem also vanishes. Inflation stretches space so dramatically that any initial curvature becomes almost impossible to detect. Just as the surface of a balloon looks flatter as it grows larger. And the monopole problem fades away because any exotic particles produced early on would have been diluted to near nothing by the vast expansion. Inflation didn't just fix details. It changed how physicists understood the early universe. Instead of beginning in a finely tuned, perfectly balanced state, the universe could start out messy. Inflation would do the work of smoothing it out, but inflation did not last forever. As this rapid expansion ended, something else happened, a process known as reheating. The energy that had been driving inflation was released, transforming into particles, radiation, and heat. In a sense, inflation prepared the stage, and reheating filled it. The hot, dense universe we usually associate with a Big Bang came after inflation, not before it. What we call the Big Bang may be better understood as the moment inflation ended. This idea brought clarity, but it also raised new questions. If inflation happened once, could it happen again? Some models suggest that inflation may be ongoing in different regions of space, producing many universes rather than just one. This possibility, sometimes called the multiverse, remains speculative. It's not something we can currently test, and it isn't required to explain our universe. What matters here is simpler. Inflation provides a natural explanation for why the universe looks the way it does, why it is smooth, why it is flat, why it is so vast. Most importantly, inflation tells us that the universe grew large before it grew complex. Size came first. Structure came later. By the time inflation ended, the universe was enormous, but still simple. Hot, uniform, filled with energy, but not yet organized into anything familiar. The stage was set, but a universe full of particles still needed one crucial ingredient. After inflation ended, the universe was enormous, but strangely weightless. It was filled with particles and energy, moving at nearly the speed of light. Yet almost nothing had mass. Without mass, there was no gravity strong enough to pull matter together. No way for particles to slow down. No foundation for stars, planets, or anything solid. To understand what changed, physicists use an idea called symmetry. In the earliest moments, the laws of physics were highly symmetrical. All particles behaved in similar ways. Nothing was heavier than anything else. The universe was balanced, but fragile. As the universe cooled, that perfect balance broke. This process is known as symmetry breaking. It's similar to what happens when liquid water freezes into ice. Above a certain temperature, everything looks the same. Below it, structure suddenly appears. At a critical moment, a new ingredient filled the universe: the Higgs field. The Higgs field is not a force. It doesn't push or pull. Instead, it is a background field that exists everywhere in space, even in complete emptiness. A common way to picture it is a crowded cocktail party. Some people can move through the room easily, barely slowed at all. Others struggle to move, constantly bumping into conversations. Particles behave in a similar way as they move through the Higgs field. Those that interact strongly with it become difficult to move, and we perceive that resistance as mass. particles that barely interact remain light and fast. Mass, in this view, is not something particles carry from birth. It's something they acquire by interacting with their environment. When the Higgs field settled into its stable state, mass effectively turned on. Particles that had once raced freely through space began to slow down. Gravity, which had existed all along, finally had something substantial to work with. For decades, this idea remained theoretical. Then, in 2012, experiments at the Large Hadron Collider confirmed the existence of the Higgs boson, the particle associated with vibrations of the Higgs field. It was a milestone moment. Not because it added a new particle to the list, but because it confirmed the mechanism that gives matter its weight. There is an important subtlety here. Most of the mass of everyday matter does not come directly from the Higgs field. For example, the proton's mass comes largely from the energy binding its quarks together, a consequence of the strong nuclear force. But without the Higgs field giving quarks their basic masses in the first place, that binding energy could not exist. In that sense, the Higgs field provides the foundation on which all other mass is built. Once mass existed, the universe changed character. Energy could condense. Particles could slow down. Clumps of matter could begin to form instead of flying apart. For the first time, the universe had weight. It could bend space more effectively. It could respond to gravity in a lasting way. This was another quiet turning point. The universe was no longer just hot and expanding. It was becoming heavy, stable, capable of building complexity over time. With mass in place, gravity finally had something to work with. And once mass existed, the universe had to decide what would survive. Once mass existed, the universe began to follow rules that could be measured. Those rules are written into a small set of numbers, values physicists call fundamental constants. They determine how strong forces are, how particles interact, and how structures hold together. What makes these numbers remarkable is not just their importance, it's how specific they are. In physics, this is known as fine-tuning. These constants are not derived from deeper principles we fully understand. They appear to be set, and even tiny changes to their values would have dramatic consequences. Consider gravity. If gravity were slightly weaker, matter would struggle to clump together at all. Gas would drift apart faster than it could collapse. Stars and galaxies would never form. If gravity were slightly stronger, the opposite problem appears. Matter would collapse too quickly. The universe would tear itself into dense clumps long before stable structures could emerge. Then there is electromagnetism. This force governs how electrons bind to atomic nuclei. Change its strength even a little, and atoms themselves become unstable. Chemistry, the basis of all complex matter, simply fails. The strong nuclear force is even more delicate. It holds protons and neutrons together inside atomic nuclei. If it were slightly weaker, nuclei could not form at all. If it were slightly stronger, nearly all hydrogen would fuse immediately, leaving no long-lived fuel for stars. These examples often sound philosophical, but they are not. They are results of straightforward physical calculations. What's important is what fine-tuning does not mean. This is not about the universe being carefully adjusted for life. Life comes much later. Fine-tuning is about whether structure can exist at all, whether matter can organize instead of dissolving back into chaos. Physicists have offered several ways to think about this. One possibility is simple chance. Simple. The constants could have taken many values. And we observe these ones because they happen to allow a stable universe. Another idea is the anthropic principle, the notion that observers can only exist in universes where conditions permit observation. Some theories go further, suggesting a vast multiverse, where different regions have different physical constants. In that picture, fine-tuning is a selection effect rather than a mystery. These ideas remain speculative. None has been proven, and none is required for what comes next in the story. Because fine-tuning by itself does not build the universe. It only defines a narrow window in which building is possible. The numbers set the stage, but they do not decide the outcome. What truly matters is what happens as the universe continues to cool. When energy drops, reactions slow, and certain processes lock in permanently. At that point, the universe stops adjusting its options. Choices are made, paths close, and the first irreversible decision happened when the universe began to cool. As the universe continued to expand, it continued to cool. At these early times, temperatures were still high enough for particles to collide constantly. Quarks combined to form protons and neutrons, the building blocks of atomic nuclei. And for a while, those two particles were not fixed identities. Through the weak nuclear force, protons and neutrons could transform into one another. A proton could become a neutron could become a proton. The universe allowed both directions, freely and repeatedly. As long as the universe remained hot and dense, this balance continued. But cooling changes everything. As temperature dropped, the weak nuclear force began to lose its grip. The reactions that converted protons and neutrons slowed down. Eventually, they became too rare to matter. This moment is known as freeze-out. From that point on, protons and neutrons were no longer freely interchangeable. Their relative numbers were locked in. Here, a small difference made a lasting impact. Neutrons are slightly heavier than protons. That extra mass makes neutrons unstable when they are not bound inside a nucleus. Left alone, a neutron will decay into a proton in about 15 minutes. As soon as freeze-out occurred, free neutrons began to disappear. Some decayed into protons. Others would later become bound inside atomic nuclei. But the balance had shifted. By the time the universe settled into its next stage, the outcome was clear. For every 7 protons, there was roughly 1 neutron. That simple ratio may not sound dramatic, but it quietly shaped everything that followed. Protons would later form hydrogen atoms. Neutrons paired with protons would form helium and heavier nuclei. The relative abundance of these particles determined how much hydrogen remained, how much helium formed, and how stars would eventually burn their fuel. This was not a choice made for life. It was not a preference. It was the result of timing, temperature, and the slowing of a single force. Once the universe cooled past this point, and there was no going back. The reactions had stopped. The numbers were set. From here on, the universe could only work with what it had. What makes this moment remarkable is how quiet it was. No explosion marked it. No signal announced it. Nothing dramatic happened on the outside. And yet, this invisible transition fixed the basic inventory of matter for the entire cosmos. Had the balance shifted slightly, had neutrons remained stable a bit longer or decayed a bit faster, the chemical future of the universe would have looked very different. Freeze-out was not a moment of creation. It was a moment of commitment. The universe stopped adjusting its options and accepted the consequences. And even with the right particles now in place, something essential was still missing. By this point, the universe had mass. It had particles. It had numbers locked into place. And yet, there was still a deeper problem. According to the laws of physics, matter and antimatter are created together. For every particle of matter, there should be a corresponding particle of antimatter. Identical in mass, opposite in charge. When matter and antimatter meet, they annihilate each other. They vanish, leaving behind pure energy, usually in the form of light. If the universe had created matter and antimatter in perfectly equal amounts, the outcome would have been simple. Everything would have destroyed everything else. After the briefest moment, the universe would have been filled with nothing but radiation. No atoms, no stars, no galaxies. And yet, that is not what happened. When we look around the universe today, we see matter everywhere and almost no antimatter at all. Somehow, matter gained the upper hand. The difference was incredibly small. For roughly every billion particles of antimatter, there was one extra particle of matter. That single leftover particle survived annihilation. And over time, those survivors became everything we see. The question is not why matter exists in large amounts. The real mystery is why any matter survived at all. Physicists have been searching for clues. One important hint came from an experiment led by Chen-Shung Wu in the 1950s. Her work showed that nature does not always treat left and right the same way, a violation of symmetry that had long been assumed to be absolute. Later, scientists discovered something even more subtle: CP violation. Certain particle interactions behave slightly differently for matter than for antimatter. These effects are real. They have been measured. But so far, they are not strong enough to fully explain the overwhelming dominance of matter we observe today. This leaves us with an unsettling conclusion. The universe does not appear to be perfectly balanced. At its most fundamental level, it favors matter, just enough for structure to exist. This imbalance was not dramatic. It was not intentional. It was almost invisible. But without it, nothing familiar would have formed. No chemistry, no stars, no planets, no observers to ask these questions. We exist because the universe made a tiny mistake, or followed a rule we do not yet understand. And that realization brings us to the edge of another mystery. Because the solution to this imbalance may not lie in the particles we can easily detect, it may be hidden in particles that pass through the universe almost without a trace. Particles that barely interact at all, yet may carry information from the universe's earliest moments. And that trail leads us to particles that almost never interact at all. There is a kind of particle passing through your body right now. It comes from the sun, from distant stars, from deep space, and from the earliest moments of the universe itself. These particles are called neutrinos. Neutrinos are almost ghost-like. They have extremely little mass. They carry no electric charge. And they interact so weakly with matter that trillions of them pass through you every second without leaving a trace. Because they rarely interact, neutrinos are incredibly difficult to detect. But that same property makes them uniquely valuable. Unlike light, neutrinos are not easily scattered or absorbed. They can travel straight through dense matter, through stars, and even through entire planets. That means neutrinos can carry information from places and times that light cannot reach. In the early universe, neutrinos were produced in vast numbers. They decoupled from matter extremely early, when the universe was only about 1 second old. After that moment, they began streaming freely through space. In principle, some of those neutrinos are still traveling today. They are messengers from the first second. Physicists have also noticed something curious about neutrinos. All known neutrinos appear to be left-handed. Their mirror image, right-handed neutrinos, has never been observed. Some theories suggest that these missing neutrinos may exist, but interact even more weakly than the ones we know. If so, they could help explain why matter gained an advantage over antimatter. The imbalance that allowed the universe to survive may be connected to the behavior of neutrinos in those earliest moments. To search for these elusive particles, scientists have built detectors on an extraordinary scale. One of them is the Ice Cube Neutrino Observatory, buried deep within the Antarctic ice. It watches for tiny flashes of light produced when a neutrino finally collides with an atom, a rare event, but a revealing one. Each detection is a small success. A single data point, a faint whisper from deep time. Neutrinos do not paint a clear picture on their own, but together, they offer a way to test ideas about the universe long before atoms formed, long before light could travel freely. They remind us that the early universe is not completely hidden. Some traces still reach us, quietly and continuously. The most elusive particles may carry the oldest information we can ever hope to observe. And in listening to them, we may learn not just how the universe evolved, but how it first began to take shape. And in those earliest moments, gravity may have left behind something unexpected. In the very early universe, everything looked almost perfectly smooth. If you could have hovered above it, you wouldn't have seen galaxies, stars, or clouds of gas. You would have seen a hot, expanding ocean of energy, nearly uniform in every direction. But nearly is the key word. Even in the earliest moments, the universe was not perfectly even. It contained tiny variations in density, faint ripples in how matter and energy were distributed. Physicists call these density fluctuations. Most of these fluctuations were small. Over time, they would become the seeds of galaxies and clusters. But in some models, a few fluctuations could have been unusually strong. If a region became dense enough, gravity could have taken control immediately, collapsing that region before anything like a star had time to form. That leads to a remarkable possibility: primordial black holes. These would not be black holes formed by dying stars. They would be black holes formed directly from the early universe itself. In 1971, Stephen Hawking explored this idea seriously. He pointed out that the early universe had conditions so extreme that gravity might have created black holes on very small scales, simply because matter was packed together so tightly. If primordial black holes exist, they could have come in a wide range of masses. Some might have been tiny, with the mass of a mountain compressed into something smaller than an atom. Others could have been far larger, and they may have mattered in a surprising way. When we observe the universe, we find something puzzling. Quasars, powered by supermassive black holes, appear very early in cosmic history. So early that it's difficult to explain how black holes could grow so large so quickly, starting from ordinary stellar remnants. Primordial black holes offer a potential shortcut. If some black holes formed early, they could have served as gravitational seeds. Matter would have fallen into them over time, helping them grow faster than standard models predict. In that picture, the darkness would not be an endpoint. It would be a beginning. Hawking also introduced another strange idea connected to black holes. Black holes are not perfectly black. Over extremely long timescales, they may emit a faint radiation due to quantum effects near the event horizon, a phenomenon now called Hawking radiation. This means small black holes could eventually evaporate. If primordial black holes were tiny enough, many of them might have disappeared long ago, leaving behind only subtle traces. like a vanished footprint. So how do scientists look for something like this? Not by taking a photograph. Instead, they search indirectly. One method is microlensing, watching for brief brightening events when an unseen massive object passes in front of a distant star and bends its light like a lens. Another approach is to look for unusual patterns in high-energy radiation, such as gamma rays, that could hint at black hole evaporation or early universe relics. So far, the evidence remains uncertain. Some mass ranges have been ruled out. Others remain possible, and the idea is still being tested. But the deeper point is what primordial black holes represent. They remind us that gravity was already at work in the earliest universe, not just as a background force, but as a sculptor. Even before atoms, even before stars, even before light could travel freely. We often think of black holes as destroyers, as cosmic endings. But in the earliest universe, they may have been something else entirely. They may have been among the first structures ever formed, small pockets where gravity proved it could build, not just pull apart. Even the darkest objects may have played a creative role, and gravity wasn't done shaping the universe yet. As the universe moved beyond its first second, it entered a brief but decisive phase. It was still extremely hot, still extremely dense, but it was finally cool enough for something new to happen. For the first time, protons and neutrons could begin to stick together. This moment is known as Big Bang nucleosynthesis, the formation of the universe's very first atomic nuclei. In the earliest minutes, protons and neutrons were constantly colliding. They attempted to form simple nuclei, but the environment was hostile. High-energy photons filled the universe, energetic enough to tear newly formed nuclei apart as quickly as they appeared. This created a bottleneck. Physicists call it the deuterium bottleneck. Deuterium, a nucleus made of one proton and one neutron, is the first necessary step toward building heavier elements. But for a time, the universe was simply too hot for deuterium to survive. Every time it formed, it was destroyed. As the universe expanded, temperatures continued to drop. Eventually, a critical threshold was crossed. Deuterium could finally exist without being immediately broken apart. Once that happened, events moved quickly. Deuterium nuclei began to collide with protons and neutrons, forming helium-3. Helium-3 collided again, forming helium-4, a tightly bound nucleus with 2 protons and 2 neutrons. Helium-4 was stable. Once formed, it tended to stay. Within a matter of minutes, the universe completed its first round of nuclear construction. The result was simple, but profound. By mass, the universe ended up composed of roughly 75% hydrogen and 25% helium. Tiny traces of other elements, like lithium, were produced, but only in very small amounts. Crucially, nothing heavier than lithium could form at this stage. The universe expanded too quickly. The density dropped too fast. There simply wasn't enough time or pressure to build larger nuclei. And then, almost as suddenly as it began, the process ended. After about 20 minutes, the universe had cooled too much for nuclear fusion to continue. The particles were too far apart, the collisions too rare. The universe shut down its nuclear reactor. From that point forward, the elemental composition of the cosmos was effectively frozen. This moment matters more than it might seem. Every star that would ever shine began with this recipe. Every galaxy formed from gas shaped by these proportions. Even the chemistry that would one day allow planets, oceans, and life depends on this early balance. What's striking is how early this decision was made. The universe was only minutes old. Yet, it had already determined what kinds of matter would be available for the next 13 billion years. Hydrogen would dominate. Helium would be abundant. Everything else would have to wait. Those heavier elements, carbon, oxygen, iron, would not appear until much later, forged inside stars and scattered by supernovae. But without this initial nuclear foundation, none of that later chemistry would be possible. Big Bang nucleosynthesis did not create complexity. It created constraints. It limited what the universe could work with. And in doing so, it quietly shaped everything that followed. By the time this brief window closed, the universe had settled into a long, quieter phase. No more nuclear reactions, no new elements, just simple nuclei drifting through expanding space. Those simple elements would someday build everything else. And yet, even though nuclear chemistry had paused, chemistry itself did not end there. After Big Bang nucleosynthesis ended, the universe became a much quieter place. The nuclear reactions had stopped. The elemental inventory was simple. Almost everything was hydrogen and helium, drifting through expanding space. There were no stars, no planets, no solid surfaces, just gas, slowly cooling. At first glance, this might seem like a chemical dead end. Without heavier elements, without stars to provide energy, it's natural to wonder whether chemistry had to wait. But it didn't. The next question the universe faced was a subtle one. When did the first molecule appear? A molecule is more than just a collection of particles. It's a structure, atoms bound together in a stable way. It's the foundation of chemistry and eventually of biology. For a long time, scientists assumed that molecules could not form until much later, after stars had ignited and forged heavier elements. But careful calculations suggested something surprising. Even with only hydrogen and helium available, one simple molecule could form. It was not water. It was not molecular hydrogen. It was something far more fragile. The helium hydride ion, written as He+, this molecule forms when a helium atom binds briefly with a proton. It's an odd pairing, unstable, easily broken, and short-lived. But under the right conditions, it can exist. In the early universe, those conditions were briefly met. As the universe cooled further, helium nuclei captured free protons, forming helium hydride ions. These ions didn't last long, but they mattered. He+ is often described as the first molecular stepping stone. It helps trigger reactions that lead to the formation of molecular hydrogen, the most important molecule for cooling gas clouds and allowing structure to form later on. In other words, the universe didn't jump straight into complex chemistry. It eased into it. For decades, helium hydride was predicted by theory, but never directly observed. It was simply too fragile and too difficult to detect. That changed in 2019. Astronomers used an airborne observatory known as SOFIA, a telescope mounted inside a modified aircraft, to observe a planetary nebula called NGC 7027. There, in the infrared spectrum, they finally detected the signature of helium hydride. It was a quiet confirmation of a long-standing prediction. The universe's first molecule had been found. This discovery mattered for more than historical reasons. It confirmed that astrochemistry began earlier than we once thought. Long before stars lit up the sky, the universe was already experimenting with chemical bonds. That realization changes how we think about cosmic complexity. Chemistry did not wait for stars. It waited only for the right conditions. The ingredients were already present: hydrogen, helium, time. What followed was slow, delicate, and easily disrupted. Molecules formed and broke apart. Energy flowed in subtle ways, but the direction was set. The universe had crossed another quiet threshold. From this point on, gas could cool more efficiently. Cooling allowed matter to clump. Clumping allowed gravity to gain traction. Every later step, star formation, galaxy formation, the creation of heavier elements, depended on this early chemical foothold. It's important to keep the scale in mind. This was not a dramatic transformation. There were no bright flashes, no sudden structures, just rare molecules forming in a vast, dark sea. And yet, without this step, nothing familiar could follow. The first molecule was not impressive by human standards. It was weak, temporary, easily destroyed. But it marked a profound shift. The universe was no longer just a collection of particles and forces. It was beginning to assemble structures that could store information, transfer energy, and evolve over time. In that sense, chemistry did not begin as a reaction. It began as a possibility. A possibility the universe was finally ready to explore. Even so, the cosmos was still very different from the one we know today. Light did not yet travel freely. Radiation was constantly scattered by charged particles. The universe remained opaque, like a fog that no beam could fully cross. The chemical groundwork had been laid, but the lights were still off. And until the universe became transparent, its earliest chapters remained hidden from view. But the universe was still opaque to light. For hundreds of thousands of years after the first nuclei formed, the universe remained strangely dark. Not because there was no light, but because light could not travel freely. At that time, the universe was filled with a hot, dense plasma. Electrons moved freely. Atomic nuclei drifted among them, and every time a photon tried to pass through, it was immediately scattered. Light bounced endlessly, trapped in a cosmic fog. As the universe continued to expand, it continued to cool. Temperatures fell. Collisions became less violent. Then, about 380,000 years after the beginning, the universe crossed another quiet threshold. The temperature dropped to around 3,000 Kelvin. At that point, electrons could finally attach themselves to atomic nuclei without being instantly knocked loose. For the first time, neutral atoms formed, mostly hydrogen, with some helium mixed in. This moment is known as recombination. It's a slightly misleading name, since electrons and nuclei had never combined before. But the effect was real. With free electrons suddenly gone, photons were no longer scattered at every step. The fog lifted. Light was released. Those photons began traveling in straight lines through space, largely undisturbed. And many of them are still traveling today. As the universe expanded, that ancient light stretched with it. Its energy dropped. Its wavelength grew longer. What began as intense radiation has cooled into a faint glow, now detectable as microwaves. This is the cosmic microwave background, the CMB. It fills the universe in every direction. It has a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. And it is one of the strongest pieces of evidence we have for the universe's hot, dense origin. The story of its discovery is almost accidental. In the 1960s, two engineers at Bell Labs, Arno Penzias and Robert Wilson, were working with a sensitive radio antenna. They kept detecting a persistent background noise. No matter where they pointed the antenna, the signal remained. They cleaned the equipment. They checked for interference. They even removed pigeons that had nested inside the antenna, along with what they politely described as pigeon debris. Nothing helped. At the same time, a group of physicists led by Robert Dicke was preparing an experiment to search for relic radiation from the early universe. When the two groups connected, the mystery became clear. The noise was not a problem. It was a discovery. The universe itself was speaking. Since then, satellites such as COBE, WMAPI, and Planck have mapped the CMB in extraordinary detail. They revealed tiny variations in temperature, anisotropies, at the level of 1 part in 100,000. Those faint patterns are not random. They are the imprints of early density fluctuations, the same ripples that would later grow into galaxies and clusters. The CMB is often called the universe's baby picture. Not because it shows stars or planets, it doesn't, but because it captures the universe at the moment it first became visible. There is a quiet twist here. The oldest light in the universe is also among the coldest. It has traveled for nearly 14 billion years, losing energy as space itself stretched. What was once searing heat now feels like a whisper. And yet, that whisper carries an enormous amount of information. It tells us that the universe was once hot and dense, that it expanded, that it cooled, and that its early structure matches our best physical models with remarkable precision. For the first time in this story, we are no longer relying on theory alone. We are looking at direct evidence, a photograph of the universe when it was still young. But this picture also reveals a limitation. The CMB shows us a universe that is smooth and simple. It does not yet show stars. It does not show galaxies. It does not show the structures that would come to dominate the cosmos. Light alone could not build those structures. Something else had to guide matter as it slowly began to clump and collapse. And that is where the final, unseen ingredient enters the story. But light alone was not enough to build structure. After recombination, the universe entered a long, quiet stretch. Space had become transparent. Light could finally travel freely. And yet, there were still no stars, no galaxies, no shining points in the dark. This period is known as the Dark Ages. The universe was filled almost entirely with hydrogen and helium gas, drifting slowly through expanding space. Everything was calm, cold, patient. If the universe were made only of the matter we can see today, this calm might have lasted forever. Ordinary matter alone is not very good at forming structure. It moves too fast. It spreads out. It struggles to clump together strongly enough to ignite stars. Something else was needed. That unseen ingredient is dark matter. Dark matter does not emit light. It does not absorb light. It does not interact with electricity or magnetism. It reveals itself only through gravity. The first clues appeared nearly a century ago, when astronomers noticed that galaxies and clusters behaved as if much of their mass was missing. Later, careful measurements of galaxy rotation showed the same result again and again. Stars far from galactic centers were moving too fast to be held together by visible matter alone. The conclusion was unavoidable. Most of the matter in the universe is invisible. Only about 15% of all matter is the kind that forms stars, planets, and people. The rest, roughly 6 times more, is dark matter. In the early universe, dark matter began to clump first. Because it does not interact with light, it could cool and collapse earlier than ordinary gas. Over time, it formed vast gravitational frameworks, invisible structures stretching across space. Ordinary matter followed. Hydrogen and helium gas slowly fell into these gravitational wells, gathering and thickening. Where the pull was strongest, gas clouds grew denser. Eventually, much later, the first stars would ignite. But during the Dark Ages, none of that had happened yet. The universe was still quiet. Dark matter was already at work, shaping the future in silence, long before the first light appeared. And that is the deeper pattern of this story. From the beginning, the universe did not rush. It unfolded in stages. Each step prepared the next. Forces separated. Particles survived. Atoms formed. Light was released. Structures quietly assembled. Nothing needed to be watched. Nothing needed to be guided. The universe knew what to do. It kept building slowly and steadily, whether anyone was there to see it or not. The universe is still unfolding, but tonight, you don't have to follow it. Everything that needed to happen already did. You are safe. The universe is quiet tonight, and you can rest.